Hi, I'm Girish Srinivasan. I would like to give you an overview of our work from the Center for 3D MR Research at the University of Illinois, Chicago. We have created a novel propeller K-space sampling strategy that is built based on a gradient and spin echo sequence in order to produce high-resolution, artifact-free MR images. This sequence that we name SteerProp can be particularly be applied to high-demand applications. In this paper, we demonstrate its use for acquiring high-resolution T2 weighted images as well as diffusion images. The motivation for our work arises from the increasing use of propeller-style K-space sampling strategy in routine clinical applications. Originally, the propeller K-space coverage was implemented based on a fast spin echo sequence. Although the fast spin echo based propeller provided excellent robustness against off-resonance effects, it suffered from data acquisition efficiency challenges. In order to alleviate this challenge, EPI-based propeller was introduced. A couple of different variations, namely the short axis propeller EPI and the long axis propeller EPI, were introduced. EPI propeller, though, was sensitive to off-resonance effects. Subsequently, Turboprop, a gradient and spin echo based sequence, was introduced that combined the merits of both FSC propeller and EPI propeller. Additionally, Turboprop also improved motion robustness using wider blades. More recently, XProp, an alternative GRASE propeller sequence, was introduced. I will discuss about XProp in comparison with our technique of SteerProp later. As a quick background, let's first take a look at the fast spin echo based propeller implementation. The diagram on the top shows a segment of a single TR of the fast spin echo propeller sequence. Each spin echo acquires a separate line of K-space. At the end of one TR, an entire strip of lines are acquired, and the number of lines in this strip, or which is called the blade, is equal to the echo train length. As we move through subsequent TRs, the blades are rotated through an angular region of pi to cover the complete K-space. As you can see here, the central region of the K-space is acquired by every blade, and this inherently enables the sequence to be robust to motion. The sequence also does not suffer from any adverse phase sensitivity effects arising from gradient echoes. Due to the redundancy of the central region of K-space, the data acquisition efficiency does get to be long. Let's now take a look at the gradient and spin echo based turbopropeller sequence. In a turbopropeller, which is built upon the gradient and spin echo GRASE sequence, each spin echo is divided into multiple gradient echoes. In the figure, we see a segment of a sequence of a single TR where each spin echo consists of 3 gradient echoes. And each gradient echo is used to acquire a separate line of K-space. As we move through the different spin echoes, multiple lines are acquired within a single blade, and at the end of a TR, we have one single wide blade that is completed. Similar to the FSC-based propeller, we do apply a rotation and then complete the rest of the K-space acquisition. As you can see here, this sequence combines the merit of both an FSE and EPI based sequences, and it also improves the robustness to motion because of significantly wider blades. Also, due to wide blades, the number of blades required to complete the entire K-space is reduced and thus improves the acquisition efficiency compared to fast spin echo based propeller. The combination of an FSC and EPI based sequences does induce phase inconsistencies within a blade. The specific goals of our work was to design an alternative GRASE-based propeller sequence that reduced acquisition times compared to FSC propeller, provided robustness against off-resonance effects compared to EPI propeller, and further improved the data acquisition efficiency compared to turbopropeller. And this is what we created as SteerProp. Let's now take a look at the details of the SteerProp pulse sequence design. A segment of a single TR of the SteerProp sequence is shown in this diagram. Similar to turboprop, SteerProp is also a GRASE-based sequence. In our implementation, we have used 3 gradient echoes for every spin echo. Each gradient echo acquires an independent line of K-space, but unlike turboprop, these lines are distributed across different blades as shown in the figure below. As we move through the spin echoes in the TR, additional lines in each of the 3 blades are acquired as shown. At the end of a TR, we complete the acquisition of 3 full blades. These 3 blades, as you see, are positioned adjacent to each other during the process of rotation. As we move through subsequent TRs, we cover the K-space 3 blades at a time. Let's now take a look at the specific mechanism of how the steering is performed and the design of the steering gradient pulses. We will focus on a single segment of a spin echo and look at the different pulses and the corresponding K-space trajectory. Within a 180-degree refocusing RF pulse, what we see here on the phase encoding GY gradient is a cyan-colored pulse that acts as an initial phase offset, followed by a blue readout gradient that helps in acquiring the first line of K-space. This is followed by what we call as the steering blip or the blip gradients, shown in brown here, that help in moving the K-space trajectory location from the end of the first line of K-space to the adjacent blade to be acquired next. The subsequent readout that is shown in red acquires the second line of K-space in the second blade. This is followed by another steering blip gradient that is shown in black that helps in moving the K-space to the third blade, and finally the third line of K-space is acquired as shown in green. Before this next subsequent refocusing RF pulse, a rewinding pulse is designed in order to bring the phase back to the KX-KY direction to satisfy the CPMG condition. This completes the single spin echo segment and completes the acquisition of 3 lines of K-space within the spin echo. As we move through subsequent spin echoes, similar additional lines for each of these 3 blades are acquired. Eventually, with the end of the TR, 3 entire blades is completed. Here is a look at the equations for the parameters for the gradient design. Figure A shows the horizontal blade that is parallel to the KX axis, followed by blades shown in B and C that have an angle of theta and 2 theta respectively. The initial phase encoding gradient played at the beginning of the gradient echo train sets up the K-space location at the beginning of the line B1. After the acquisition of the line B1, the blip gradient pulses gx theta and gy theta help in moving the K-space position from the location phi B1 to the start of the acquisition of line B2 in the second blade as shown in figure B. Similarly, gx2 theta and gy2 theta helps moving the K-space location from the end of the line B2 to the beginning of line B3. Finally, a pair of rewinding pulses GXR and GYR helps to return the K-space trajectory to the KX-KY axis as if there was no steering done. This helps in positioning for the subsequent spin echo acquisition. A comparison of the different K-space sampling strategy for a single TR is shown in the figure below. The first one is the fast spin echo based propeller, where each spin echo is used to sample a single K-space line. One blade is completed for every TR. The subsequent diagrams show 3 different variations of the GRASE-based propeller implementation, namely Turboprop, X-Prop, and Steer-Prop. With the use of 3 gradient echoes for each spin echo, in the case of Turboprop, all the 3 gradient echoes are used to sample the same widened blade. In the X-Prop case, the X-Prop assigns odd echoes shown by solid lines and even echoes shown by dashed lines into orthogonal blades. This creates 6 blades which are distributed evenly over an angular range of pi. In our implementation of the Steer-Prop, the 3 blades in every TR are distributed into a narrow angular range by placing them adjacent to each other. As we can see, the increment between the blades in X-Prop is larger, and hence the steering gradient has to be larger. The smaller steering gradient in the Steer-Props allows for the use of shorter echo spacing compared to the X-Prop. The Steer-Prop sequence was implemented and evaluated on 2 General Electric MRI scanners operating at 1.5 Tesla and 3 Tesla. And specifically at 1.5 Tesla, we used 2 different hardware configurations. All image reconstruction and post-processing was implemented using custom program written on MATLAB and C on a Unix environment. Let's now move from the pulse sequence design to the motion correction and phase error correction mechanisms. The steer prop sequence is primarily subjected to three different kinds of phase errors, and they must be accounted and corrected for in order to obtain high-resolution artifact-free images. The figure here shows a segment of the steer prop sequence with two subsequent TRs or shots. Any phase errors that are introduced between the two TRs, primarily arising due to motion, is termed as the intershot phase error. Similar to EPI, the echoes within a gradient echo train can have inconsistent phase errors, or basically EPI type phase errors, that lead to the inconsistencies among the blades acquired within a single shot. This is referred to as the inter-blade phase error. Finally, the K-space lines within a blade are acquired from different spin echoes, and these are subjected to FSE type phase errors, and this is called as the intra-blade phase error. As mentioned before, the intershot, interblade, and intra-blade phase errors needs to be accounted for and corrected for in order to obtain high-resolution artifact-free images. The intra-blade phase errors can be estimated and corrected for in two steps. The first one as a part of the pulse sequence, followed by the reconstruction mechanism. In the pulse sequence, two additional spin echoes in the echo train are acquired that are not phase encoded. The constant and the linear phase obtained from the non-phase encoded lines are estimated and are used in the phase encoded line for correction. Any low frequency motion is corrected using a typical propeller style K-space correction, where the K-space blade is compared against a windowed version of this blade, and the difference is corrected for in the final blade to be used. Since all the blades acquired within a single shot intersect at the central region of K-space, this redundancy in data can be exploited to do phase correction, similar to in-plane motion phase correction in the original propeller implementation. This data redundancy can be applied and used to correct both for interblade and intershot phase errors. Thus, the image reconstruction and the phase error correction pipeline consists of obtaining the raw data, performing intra-blade phase error correction, followed by intershot and interblade correction, a through-plane motion correction, and finally gridding and inverse Fourier transform. This pipeline and process was implemented in MATLAB and C through custom program. To demonstrate and evaluate the performance of steer prop, 4 main experiments were set up. The first one was to acquire images using steer prop and a comparable FSC prop on a GE structured BQA phantom, both at 1.5 Tesla and 3 Tesla scanners. This experiment was followed by applying steer prop to a healthy volunteer and acquired at 1.5 Tesla. To assess the sensitivity to motion and the performance of steer prop in motion situations, A third experiment was set up to compare motion sensitivity against standard FSC sequence, FSC propeller sequence, as well as the steer prop sequence. Finally, in typical single-shot EPI sequence, there are severe substantial distortions due to orientation-dependent susceptibility effects, primarily in non-axial planes. So we conducted experiment to compare the performance of steer prop against single-shot EPI on both axial and non-axial planes. The results from imaging on the GE structured DQA Phantom, both at 1.5 Tesla and 3 Tesla, showed that steer prop can produce high-quality images comparable to the ones obtained using FSC propeller. The signal-to-noise ratio measured using the location shown indicated a 30% reduction in steer prop compared to FSC propeller. It must be noted, though, that the steer prop images were acquired in just 1/3 the scan time compared to FSC propeller. Although an overall 30% lower SNR was seen on steer prop, the normalized signal-to-noise ratio for steer prop was higher than FSC propeller. We did observe some minor streaking artifacts at the central region of the Phantom in steer prop images. We believe this might be because of magnetic susceptibility effects associated with the Phantom geometry. On volunteers, images were obtained at 1.5 Tesla for both T2 weighted images and diffusion weighted images. The FSC propeller and the steer propeller again showed very similar image quality, while the steer prop was acquired at 1/3 the scan time. In the third experiment, for assessing the motion robustness, the volunteer was asked to perform a predetermined head motion task, and during this procedure, a standard FSC sequence, FSC propeller sequence, and the steer prop sequence was used for the acquisition. As shown, the images acquired from the FSC sequence showed severe ghosting artifacts due to motion. The motion artifacts were corrected in the images from both FSC propeller as well as steer propeller. This steer propeller again had image quality that was comparable to the ones from FSC propeller, while the steer prop images were acquired in just 1/3 the scan time. This experiment was performed at 3 Tesla. In the final experiment, we compared the performance of steer prop with respect to single-shot EPI, particularly on non-axial planes. The bottom row images shows the acquisition from single-shot EPI, and images on the sagittal, coronal, and oblique planes show significant gross distortion. The steer prop, on the other hand, does not show any artifacts and is devoid of any of these imperfections. Thus, we can see that steer prop can be used as an alternative sequence even compared to single-shot EPI on all planes. In summary, what we have shown in our project in this paper is the demonstration of our novel steer propeller, which is an alternative GRASE-based propeller sequence, which has an integrated mechanism for phase error and motion error correction, and is demonstrated to produce high-resolution artifact-free images at 1.5 Tesla as well as 3 Tesla. The sequence has excellent robustness to motion, and it can be used to acquire images across axial and non-axial planes. The steer propeller sequence is faster than the standard FSC-based propeller sequence by at least a factor of 3. As future work, in the pulse sequence design, we can enhance the data acquisition efficiency even more by incorporating parallel imaging support. The sequence can also be applied and evaluated on non-neuroanatomies. We also believe we can further optimize the image quality by using a B0 field map for off-resonance correction, as well as applying and integrating a coil intensity correction mechanism. We would like to thank and acknowledge the NIH and the CCTS University of Illinois for the grant and funding support, other members of the Center for MR Research and the Department of Bioengineering, fellow researchers at the Center for MR Research, as well as other faculty members at UIC for their guidance and support. Thank you very much for your time.